In the previous section, we saw linear search and binary search. In both these searching techniques, search time is dependent on the number of elements. Similarly, in different search trees also, the search time is totally dependent on the number of elements, and many key comparisons are performed. In this section, we'll see a technique in which less key comparisons are performed and searching can be done in almost constant time, which means that search time of an element will not depend on the total number of elements. Now suppose we have some keys that are in the range 0 to n minus 1. To store these keys and their associated records, what we can do is we can take an array of size n and store the records in this array. So a key with value I can be stored at index I of this array. For example, if the value of key is 2, then it is stored at index 2. If the value of key is 7, it will be stored at index 7, and so on. Now let's take an example of student records. Suppose each student record contains student's roll number, student's name, and student's marks. Now this roll number will be unique, so we can take this roll number of the student as a key. These roll numbers are in the range 1 to 99, so we can take an array of size 100 and store these records in this array. So this record with key 10 is stored at index 10. This record with key 97 is stored at index 97. This record with key 12 is stored at index 12. This record is stored at index 4, and so on. Now when we have to search for a student with roll number k, we can directly go to index k of this array and we can get the record. For example, if we have to access record of a student with roll number 12, we can just go to index 12 of this array and access the record. So by using this method, we can access any record in constant time, and there were no key comparisons. This method is known as direct addressing, and this array is called direct address table or direct access table. Now the clear advantage with this method is that searching is order of 1. But the problem in this method is that it can be used only when the set of possible keys is small. Now let's see why we can't use this method when the set of possible key values is large. Now suppose these student roll numbers are some 5-digit numbers instead of small numbers. So now we have these 5-digit roll numbers. Now the greatest roll number possible is 99,999. If we use this direct addressing method, then we'll need an array whose last index is this. So we need an array of size 100,000. Now out of these 100,000 locations of this array, only 100 locations would be used for storing these student records. So it's clearly lot of wastage of space. So when the set of possible key values is much more than the number of keys, this direct addressing method is not feasible. And in practice, this is generally always the case. So this direct addressing method is rarely used. In the previous lecture, we discussed direct addressing, in which we use the value of the key itself to select a slot in the table. Now we'll modify this direct addressing method so that space is not wasted and still we can use the value of the key to find out its address in the array. Now to do this, we'll require some sort of procedure that can convert the key into an integer within a given range. And we'll use this converted value as the index of the array. So basically we need a procedure that can convert a big number to a small number. For example, where we need to convert these 5-digit roll numbers into smaller numbers that lie in range 0 to 99. If we do this conversion, then we can take an array of size 100 and store the student records in that array. So what we'll do, instead of taking the key equal to the array index, we'll take the new converted value as the index of the array. This process of converting a key to an address is called hashing. And to do this, we need a hash function. So what is a hash function? It is a function that is used to convert a key value to an address. This hash function will take a key as an input and it will return hash value of that key. And this hash value is used as the address for storing the key in the array. Now keys can be of any types like integers, strings, but this hash value will always be an integer because it denotes the address where we need to store the record. Now mathematically we can write a hash function like this, where h is the hash function, k is the key and a is the hash value of the key k. In direct addressing, we stored the key k at index k of the array. But now we'll store the key k at index a of the array. This a is also known as this key's home address. So this hash function maps the key to a smaller integer, which is used as the address. By address we mean index of the array. So we can say that hash function h is a mapping from universe of keys to the slots of a hash table. And this process of generating an address from a key is called hashing the key. And a hash table is the array in which the records are stored and retrieved using this process of hashing. Now let's see the procedure for storing and retrieving records using a hash function. First we create an array A of size m. This array A is our hash table and it has slots from 0 to m-1. Then we'll choose a hash function h, which is a mapping from keys into integers from 0 to m-1. Now to insert a record in the hash table, we'll generate an address by applying hash function to the key and then we'll insert the record at that address. Now to retrieve a record, we'll apply the same hash function to the key and then access the record at the address given by the hash function. We have seen that in direct address tables, any key k is mapped to slot ak, while here in hash tables, any key k maps to slot a hk. Now let's go back to our example of student records. Now here first we create a hash table of size 100. So it has slots from 0 to 99. Now we need a hash function that can map these keys to integers within the range 0 to 99. Suppose we take a hash function that takes a key and returns last 2 digits of that key. For example, if we have this roll number 81835, then its hash value would be 35. And so the record of this student will be stored at index 35 of this array. So using this hash function, we'll have addresses in the range 0 to 99 only. Now let's insert these records in this hash table. Hash value for this key is 11. So it will be stored at index 11 of this array. Hash value for this key is 98. So it will be stored at index 98 of this array. Hash value for this record is 5. So it will be stored at index 5 of this array. And Similarly, other records will be stored. Now, retrieving a record is also simple. If we want to access record of a student with this roll number, then first we generate the address using the same hash function. Now we can directly go to index 98 and retrieve the record. So this is how hashing is done, and records are stored and retrieved from a hash table. Now while using hash function to generate addresses, we can encounter a problem. In the next lecture, we'll see what that problem is. In the previous lecture, we used this hash function and we stored this record at index 11, this record at index 98, this record at index 5, and so on. Now this record has to be stored at index 98, but this slot 98 is already occupied by this record. So now the problem is where to store this record. This problem occurred because our hash function generated the same address for these two different keys. For this key also it generated 98, and for this key also it generated 98. Now this problematic situation is called collision, and it occurs when our hash function generates the same address for different keys. This problem of collision would never occur in direct address tables because there we were using keys as addresses, and keys are unique. So we'll have unique address for each record. An ideal hash function would perform one-to-one mapping between set of all possible keys and all hash table addresses, which means that it would generate a unique address for each key. But this ideal hash function is practically not possible. So it is almost impossible to make hash functions that can totally prevent collisions. The best we can do is design a hash function that minimizes collision. Now since we cannot fully avoid collisions, we'll need some collision resolution technique. A technique that will tell us what to do when a collision occurs. We'll study about these two collision resolution techniques later in this course. Now in the next lecture, we'll see some examples of hash functions. In this lecture, we'll discuss hash functions. We have seen that a hash function is used to generate a hash address from a key. Now let's see some basic properties that a hash function should have. If we have a hash table of size m, then our hash function should generate addresses in this range 0 to m-1. A hash function should be deterministic, which means that for a given key, it must always generate the same hash address. A hash function should be easily computable. It should not take very long to compute. So the hash function should be easy and fast to compute. Next, a hash function should generate addresses such that collision is minimized, which means that it should distribute the keys as uniformly as possible. Now, if the nature of keys is known in advance, then we can choose a good hash function that gives minimum collision for those type of keys. For example, if we take social security number as a key, then taking a hash function that uses the first 3 digits is not a good idea, since the first 3 digits represent the geographical area, and so they can be same for many keys if the data is from the same geographical area, and hence there will be many collisions. So in this case, using the last 3 digits can be a better idea. Similarly, if we take date of birth as a key, then using the day of birth is a better idea than year of birth. So based on the nature of the keys, we can try to create a hash function that performs well. So we need a different approach for different type of key. In most of the cases, we don't know the nature of keys in advance. So the general approach is to take a hash function that can work such that the addresses generated are distributed randomly. There are many ways of constructing a hash function. So now we'll see some simple techniques for making hash functions. In all our examples that we discuss, we'll assume that the key is an integer. If we have keys that are not integers, then we can easily convert them into integers. For example, if we have an alphanumeric key or a string, then we can convert it to an integer by using the ASCII values of the characters. Now the first method that we'll see is truncation. It is also called extraction or digit selection. It is the simplest method for constructing a hash function. In this method, we generate an address from the key by selecting some digits from the key. For example, we can take some rightmost digits or some leftmost digits from the key as the address. Now suppose we have a hash table of size 1000 and we have to store some 8-digit keys. Now table size is 1000, so we need addresses in the range 0 to 999. We can form our addresses by selecting any 3 digits from the key, and that way we can get addresses in this range. If we decide to take the 3 rightmost digits as the addresses, then the addresses will be this. So now this key is stored at index 457, this one is stored at 436, and so on. If we decide to form the addresses by taking 2nd, 5th and 8th digits, then the addresses will be this. This method is easy to compute and is fast, but the chances of collision are more as we are not utilizing the entire search key. Now next method is mid-square method. In this method, we square the given key and then some digits from the middle of the square are taken as the address. The selection of digits depends on the size of the table. Suppose we have a hash table of size 100 and we have 4-digit keys. Then we'll need addresses in the range 0 to 99. We square these keys and then take 2 middle digits as the address. So these are the addresses. If we have a hash table of size 1000, then we can take 3 middle digits from the square. Now if the keys are very large, then this square will be even more large. So in that case, we can take a portion of the key and perform mid-square method on that portion. For example, suppose we have 9-digit keys. We can take a portion of the key which contains first 4 digits or last 4 digits of the key and then square that portion. Next we have folding method. In this method, we break the key into different groups such that the length of each group is same as that of the required address, except possibly the last group. Suppose we have a hash table of size 1000 and we have some 11-digit keys. This is one of the keys. We break it into groups of 3 digits. The last group is only of 2 digits. Now these groups of the key are shifted such that the least significant digits of all groups are in the same line, and then these groups are added. Now we can obtain the address of the key by ignoring the final carry in the sum. So the hash address for this key is 625. This method is called shift folding. We can slightly modify this method to get another method called boundary folding. In this method, we reverse all even groups before addition. So here we have reversed this second and this fourth group. Now ignoring this final carry 2, the address is 417. Now let's see division method. This is the most commonly used method for hashing keys. In this method, we divide the key by the table size and we take the remainder as the hash address. This is also called modular division method or modular hashing method. Now, if the table size is m, then any remainder will be in the range 0 to m minus 1. And therefore, hash addresses that will be generated will be within this range 0 to m minus 1. So, this method ensures that the address that we get is in the limited range of the table. In our program, we can use this operator to get the remainder. We can minimize collisions if we take the size of the table a prime number. This way we can distribute the keys evenly in the table. Now suppose we have a table of size 97 and we have these keys. So these will be the addresses. Now this modulo method can be combined with other hashing methods to ensure that addresses are in the range of the hash table. Now let's talk about the size of hash table. If we have n records, then ideally we would like to take a hash table of size n. But in many cases, the exact number of records is not known in advance. So generally the size of the hash table is different from the number of records. The number of records is generally denoted by n and the size of the table is denoted by m. The selection of the table size will depend on the collision resolution method that we use. Now let's see what is the load factor of a hash table. It is defined as the ratio between the number of records to be stored and size of the table. Now in the next few lectures, we'll study about collision resolution techniques. In the introduction lecture, we had seen that a collision occurs when a key is mapped to an address that is already occupied. Now since we cannot place this key at the address given by the hash function, we need to find an alternate place for the key. And for this, we can use one of these two collision resolution techniques, open addressing and separate chaining. First, we'll learn about open addressing. In this technique, we'll place the colliding key at some empty location inside the hash table itself. So when we find that a key is mapped to an already occupied address, we'll start searching for an empty location inside the table. We'll see three methods for finding an empty location inside the table: linear probing, quadratic probing and double hashing. First, let's see this linear probing. In this technique, we'll place the colliding key at the next empty location in the table. So suppose we have a key K and it is mapped to some address A by the hash function. Now if this address A is empty, we can place the key there. But if it is already occupied, then we'll look at the next location of the table. So we look at address A plus 1. Now if this address A plus 1 is empty, we can place the key at this address. Otherwise, we look at address A plus 2. So we keep on trying successive locations till we find an empty location where the key can be placed. And in this process, if we reach the last position of the array, then we can resume our probe from the 0th position. Now suppose we have a hash table of size 11 and a key is mapped to address 7 by the hash function. Now if this location 7 is empty, there will be no collision and we'll place the key here. If location 7 is not empty, then we look at location 8. If location 8 is also not empty, we look at location 9. If 9 is also not empty, we look at location 10. If 10 is also not empty, then we'll look at location 0. And then we look at locations 1, 2 and so on. So we search for empty locations in this sequence. So basically we are linearly probing the array and we place the key when we reach an empty location. Now we'll take a hash table of size 11 and we'll insert some keys in it. We'll use this simple hash function, and whenever there is a collision, we'll use linear probing to resolve it. Now first we have to insert key 57. It is mapped to location 2 by the hash function. This location 2 is empty, so this key is inserted here. Next, we have to insert this key 40. It is mapped to location 7. Location 7 is empty, so we insert it here. Next, 69 is mapped to location 3. 3 is empty, so we insert it here. Next, this 54 is mapped to location 10. This location 10 is empty, so we'll insert this key here. Next, we have this key 29 and it is mapped to location 7. Now, location 7 is already occupied. So, we'll look at the next location. This next location is empty, so we can insert the key here. Next, this key 76 is mapped to location 10 and location 10 is already occupied. So, we look at the next location. This next location 0 is empty, so we can insert the key here. Next, this key 35 is mapped to location 2. This location 2 is already occupied, so we look at the next location. This next location is also occupied, so we look at the next location, location 4. Now this location is empty, so we can insert the key here. Next we have to insert this key 87. It is mapped to location 10. Location 10 is already occupied, so we look at the next location. This is also occupied, so now we look at location 1. It is empty, so we insert the key here. So this was the explanation of how insertion is done in the case of linear probing. Now let's see how to retrieve a record. For retrieving a record, first we'll get the hash address by applying hash function to the key. Now if the key is not found at the hash address, then we'll search linearly after the hash address. The search is successful if we find the key, and the search is unsuccessful if we reach an empty location or we reach the position where we had started. Now for example, in this table, if we want to search for key 35, then first we apply the hash function. The hash address comes out to be 2. Now key 35 is not present at hash address 2. So now we'll sequentially search for 35 till we reach an empty location or we come back to address 2. So we look at address 3, 35 is not present here. Now we look at address 4, 35 is present here. So the search is successful. Now suppose we have to search for key 65. We get the hash address 10. Now 65 is not present at hash address 10. So we start searching sequentially. Now 65 is not present here. It is not present here, not present here, not present here, not present here. Now we have reached an empty location. It means that the search is unsuccessful. This key 65 is not present in the table. We can write the formula for linear probing like this. This h is the hash function. This t size is the size of the table. And the value of I varies from 0 to table size minus 1. Here we have done this mod table size so that the resulting address does not cross the array boundary. So while searching for an empty location, the sequence of probes would be this. First the value of I is 0, then 1, then 2, 3 and so on. The sequence of locations that we examine is called probe sequence. We have seen earlier that if we have a hash table of size 11 and a key is mapped to location 7 by the hash function, Then this is the sequence of probes. Let's verify this by using the formula. This is how we get the sequence by using this formula. Hash value is 7, table size is 11, so I goes from 0 to 10. And each time we are doing mod table size. So we get the same sequence by using this formula. Now let's look at a problem that we face in linear probing. When almost half of the table is occupied, there is a tendency of cluster formation. Now these clusters are nothing but groups of records placed next to each other. For example, in this table, we have this cluster formed by locations 10, 0, 1, 2, 3 and 4. Now because of these clusters, the search time of a key increases. Now if a key is hashed to any of these locations within this cluster, then it will be stored here at index 5 and this cluster will increase in size by 1. This problem is called primary clustering, and because of this, the number of probes required to insert or retrieve a key increases and it reduces the performance. Now once a cluster is formed, it is more likely to grow by insertion of more colliding keys. So the bigger the cluster gets, the faster it grows. For example, if we have a cluster of 10 locations, then any key mapped to these 10 locations will be added at the end of the cluster. If we have a bigger cluster of suppose 50 locations, then chances of this cluster getting bigger are more, because now any key mapped to any of these 50 locations of this cluster will be added to the cluster. So bigger the cluster gets, the faster it grows. There is also a possibility that two clusters join and form a bigger cluster. For example, in this case, suppose after some time all these locations are occupied. Then these two clusters will join and we'll have a bigger cluster. To prevent this primary clustering problem, we can use quadratic probing technique, which we'll discuss in the next lecture. In this lecture, we'll discuss quadratic probing. We have seen the formula for linear probing. In quadratic probing formula, we have I square instead of I. So in case of quadratic probing, this is a sequence of locations that will be probed. We add 1 square, then 2 square, then 3 square and so on. Now suppose a key is mapped to location 8 by the hash function. In linear probing, we tried these locations. But in quadratic probing, we'll try these locations. We are adding 1 square, then 2 square, 3 square, 4 square and so on. So in linear probing, we probed locations adjacent to the initial hash address. But here, we are probing widely separated locations. And this reduces the formation of clusters. Now we'll take a hash table of size 11 and insert some keys in it using quadratic probing. Again, we'll take this simple hash function. First, we have this key 43. It is mapped to location 10. Location 10 is empty, so we insert it here. Next, we have this key 50. It is mapped to location 6. It is empty, so we insert it here. This key 57 is mapped to location 2, which is empty, so we can insert it here. Next, this key 61 is mapped to location 6. Now location 6 is not empty. So now this is the sequence of locations that we have to try. First we have to try this location 7. This location 7 is empty, so we can insert the key here. Next we have this key 68 is mapped to location 2. It is not empty. This is the sequence of locations that we have to try. First we have to try this location 3. It is empty, so we insert it here. Now this key 30 is mapped to location 8. This location 8 is empty, so we can insert it here. Next we have this key 24. It is mapped to location 2. Now location 2 is not empty. So this is the sequence of locations that we'll try. First we'll try this location 3. It is not empty. Then location 6. It is also not empty. Then location 0. It is empty. So we insert the key here. Next we have this key 39. It is mapped to location 6. Location 6 is not empty. This is a sequence of locations that we'll try. First we try this location 7. It is not empty. Location 10. It is not empty. Location 4. This location 4 is empty. So we'll insert the key here at location 4. So this was the explanation of insertion using quadratic probing. In linear probing, we store the colliding keys near the initial collision point, and this results in primary clustering. In quadratic probing, we are storing the colliding keys away from the initial collision point. So this reduces the formation of clusters and thereby prevents primary clustering. But now we have a new problem called secondary clustering. This problem occurs because keys that hash to the same address will always probe the same locations. For example, all keys mapped to location 8 will always follow the same probe sequence. So the keys mapped to same location always follow the same location chain, and this reduces the access time. In primary clustering, clusters were formed by records which are stored next to each other. In secondary clustering, clusters are formed by records that follow the same collision chain. So here we have this cluster. Now this secondary clustering problem is less severe than primary clustering problem, because here two keys will have the same collision chain only if their initial hash address is the same. In primary clustering, different keys can have same collision chain even if the initial hash address is not same. For example, here only keys that are mapped to location 8 will follow this collision chain. Keys that are mapped to location 9, 12 or 17 will follow some other collision chain. So only keys that are mapped to location 8 will be added to this cluster. Now here, keys mapped to these locations 8, 9, 10 or 11 are following the same collision chain. So the chances of this cluster getting bigger are more, since any key mapped to any location inside this cluster will be added to the cluster. And this cluster will increase in size only when a key is mapped to this initial hash address 8. So in secondary clustering, a cluster will increase only if a new key is mapped to the same hash address as that of the other keys of the cluster. Because here clusters are formed by keys that have same initial hash address. In primary clustering, the cluster size would increase if the initial hash address of a new key lies anywhere inside the cluster. So this cluster will grow if any key is mapped to location 8, 9, 10, 11 or 12, and this cluster will grow only if a key is mapped to location 8. Apart from this secondary clustering problem, Another problem with this quadratic probing is that it can't access all the locations of the hash table. An insertion operation can fail in spite of empty locations in the table. In linear probing, an insert operation will fail only when the table is full. To reduce this problem, we can take the size of hash table to be a prime number. In that case, at least half of the locations of the hash table will be accessed. Now, both primary and secondary clustering problems can be reduced by using double hashing, which we'll discuss in the next lecture. In this video, we'll discuss double hashing, which effectively eliminates the clustering problem. We have seen linear probing and quadratic probing. And in both these techniques, we skip a constant amount each time. In double hashing, we'll skip a variable amount each time. And we'll do this by using a second hash function. This is the formula for double hashing. This is the first hash function and this is the second hash function. So we can see that here the increment factor is not constant. It depends on the key. Now if two keys are mapped to the same location by this first hash function, then it is not necessary that those two keys follow the same probe sequence, as was the case in linear probing or quadratic probing. Here the probe sequence for both the keys will be different because the increment factor will be different for both the keys. And this increment factor will be different because the value of this hash function will be different for both the keys. This was the probe sequence in linear probing. This was the probe sequence in quadratic probing. And this will be the probe sequence in double hashing. So we can see that the increment factors in both linear probing and quadratic probing are key independent. They don't depend on the key. While in double hashing, increment factors are key dependent. This is named double hashing because we are using two hash functions here. The first hash function is called primary hash function and the second hash function is called secondary hash function. An example of secondary hash function is this. Here R is a number smaller than the table size and is a prime number. Now we'll see some examples of inserting keys in a hash table of size 11 using this double hashing. We'll use this simple hash function as the first hash function and this one as the second hash function. Now first we have to insert this key 43. It is mapped to location 10. It is empty, so we insert it here. Next we have to insert this key 50. It is mapped to location 6, which is empty, so we insert it here. Next we have this key 57. It is mapped to location 2, which is empty, so we insert it here. Now we have to insert this key 61. It is mapped to location 6, which is already occupied. So now using the double hashing formula, we calculate the next probe location. And this is how we do it. This is the value given by the first hash function. This is the second hash function. 7 minus key mod 7. And the value of I is 1. And here we are doing mod table size. So we get location 8 and it is empty. So we'll insert this key 61 at location 8. Now we have to insert this key 68. It is mapped to location 2, which is already occupied. So we calculate the next probe location. It comes out to be 4 and this location 4 is empty. So we insert the key 68 here. Now we have to insert this key 30. It is mapped to location 8, which is already occupied. So we calculate the next probe location. It comes out to be 2. But location 2 is also occupied. So we calculate the next location. and this time value of I is 2. Now this next location comes out to be 7. This location 7 is empty, so we insert this key 30 at location 7. So this is how we insert the keys. Now in double hashing, there is no problem of primary or secondary clustering. This is because the keys that have same initial hash address probe different sequence of locations. For example, these keys 46, 35 and 57 all are mapped to the same hash address 2 by the primary hash function, but their probe sequences are different. While in linear probing and quadratic probing, the probe sequences for keys mapped to same address are same. So here we can see that all keys mapped to location 2 have this probe sequence, and here all keys mapped to this location 2 have this probe sequence. Now let's talk about the choice of hash functions in double hashing. The primary hash function is chosen as usual, but we should keep some things in mind while choosing the secondary hash function. Firstly, it should not be the same as the primary hash function. And second, it should never evaluate to 0. If it evaluates to 0, then the probe sequence will always remain at the initial hash address. This is the formula for calculating the probe sequences. Now here, if this value is 0, then we'll be stuck at this hash address only. Now value given by secondary hash function should be relatively prime to the table size. That is, their greatest common divisor should be 1. If this is so, we'll be able to probe the entire table. The probe sequences will visit all of the table locations. If they are not relatively prime, then there will be slots that would remain unexamined. Generally, the table size is taken as a prime number, so it will be relatively prime to all step sizes. As we have seen before, a good choice for secondary hash function is this, where R is a prime number less than the table size. This double hashing eliminates the clustering problem, but it is more complex and slower than linear and quadratic probing because it requires evaluation of 2 hash functions. So we have discussed 3 forms of open addressing techniques: linear probing, quadratic probing and double hashing. We have seen that the load factor of a table is defined as the number of records divided by the size of the hash table, and it is generally denoted by this lambda symbol. In open addressing techniques, the load factor is always less than 1, as the number of records cannot exceed the size of the table. For better efficiency, it is desirable that there are always some empty locations inside the table. So the size of the table should be little more than the number of actual records to be stored. If the load factor of a hash table becomes close to value 1, it means that the hash table has become dense. There are many occupied locations and very few empty locations. So there will be more chances of collision and the efficiency will reduce. So as the table approaches maximum capacity, load factor approaches 1 and searching becomes linear. The only solution to this problem is rehashing. In rehashing, we take a new hash table of larger size and hash all the entries to this new hash table. So leaving some locations empty in the hash table improves search time but results in a wastage of space. Therefore, we can say that it is a space versus time trade-off. In previous lectures, we have seen how to insert and search records in open addressed hash tables. In this lecture, we'll talk about deleting records in open addressed hash tables. Suppose we have this hash table of size 11. First, we'll insert some records in it using this hash function and using linear probing. And then we'll see how to delete records from it. First, we have this key 57. It is inserted here. Next, we have this key 40. Will be inserted here. Key 54 will be inserted here. Key 29 is mapped to location 7, which is not empty. So we insert it here. Key 76 is mapped to location 10, which is not empty. So we look at the next location and insert it here. Key 67 is mapped to location 1. Key 65 is mapped to location 10. Location 10 is not empty. So we look at next location, next. We insert it here. Key 35 is mapped to location 2. It is not empty. So we insert it here. So insertion of records is over. Now we have to delete this record with key 57 from this hash table. Suppose we perform this deletion by marking this location as empty. So now, like these locations 5, 6 and 9, this location 2 is also empty and we can use it to insert new records. This approach seems good, but it breaks our searching. Let's see how. We have seen that we can stop searching when we find the key that we are looking for, or when we reach an empty location, or when we come back at the location where we started searching. In this case, the search is successful, and in these two cases, search is unsuccessful. Now suppose we have to search for key 65. First we get the hash address, comes out to be 10. So we start our search from here. We go here, then here, then here. We reach an empty location. So we stop our search and we conclude that the search is unsuccessful. This location that had become empty due to deletion terminated our search prematurely and gave us false result. The 65 is present in the table, but we did not reach here because of this location that had become empty due to deletion. Similarly, if we search for key 35, we'll get wrong result. This key 35 is mapped to address 2. Now this location 2 is empty. So the search is terminated. This 35 was present in the table, but we could not find it. So we can see the culprit here is this location that had become empty due to deletion. We have taken the example of linear probing. The same problem can occur in quadratic probing and double hashing also. Now let's see what we can do to solve this problem. We'll need to differentiate between empty locations that never contained a record and empty locations that previously contained a record but now have become empty due to deletion. We can do this by maintaining a status flag, and that status can take any of these three values: occupied, empty or deleted. This flag will be equal to occupied for locations that are occupied, locations that hold records. Empty for locations that were never occupied, and deleted for locations that were occupied but now are empty. So in this table, after deleting the record from location 2, we mark this location as deleted. So these are the locations that are occupied. These are the locations that are empty. And this location that is marked as deleted was occupied before and now has become empty due to deletion. Now while searching for a key, we'll stop only when we reach a location whose status is empty. We will not stop our search if we encounter a location whose status is deleted. So now when we search for this key 65, we'll not stop here. While inserting a new record, we can stop when we reach either an empty location or a deleted location. If we don't want to take a separate status flag, we can mark a location as deleted by storing an invalid value for the key. For example, suppose -1 is an invalid value for the keys that we have taken. We can't have a key with value -1. So now when we have to delete record with this key 57 from this hash table, we can just change the key of this record to -1. Now while searching, we'll stop when we reach an empty location, and while inserting, we'll stop when we reach either an empty location or a location that has a record with key -1. In this lecture, we'll see how to implement hash tables using open addressing technique. In our hash table, we'll store records of students. So we have made the simple class student record, which has these two members, student ID and student name. We'll use this student ID as the key. And we'll assume that -1 is not a valid student ID. So whenever we have to delete a record from the hash table, we'll just change its student ID to -1. Now this is the constructor, get student ID method, set student ID method, and toString method. Now this is our hash table class. We implement our hash table with the help of this array of type student record. This member M denotes the size of the array or the hash table, and this member N denotes the number of records. These are the two constructors of this class. In this constructor, we are passing the size of the table. And if the size of the table is not provided while creation of object, then we'll create a table of size 11. And this method, hash, implements the simple hash function that we'll use for mapping the keys to array indices. Now let's see this method insert. We've used linear probing technique here. We have to insert this new record into the table. First, we extract the key from the record. Now with the help of this hash function, we find the hash value. We take this variable location and initialize it to this hash value. Now we come to this for loop. In this for loop, I goes from 1 to m-1. We are using linear probing here. So this is how we calculate the next probe location. We'll insert the new record at this location if the location is null, or if the student record at this location has a student ID -1. After inserting this new record, we increment this variable n, which denotes the number of records, and then we'll return. If we find the key somewhere, then we'll throw this exception. If the control comes here, it means that we have visited the whole table and did not find any empty location. So we print this message. Now let's see this method search. This method will search for this key in the table and it will return the record with this key, and if the record is not present, then it will return null. Now this method is like the insert method that we have just seen, but here we will not stop when we reach a location whose student ID is -1, and we have discussed the reason for this in the previous lecture. We'll stop only when we reach an empty location. If we find the key, then we'll return the associated record. We are using linear probing, so this is how we'll calculate the next probe location. If the control comes here, it means that we have visited the whole table and the key was not found. So we return null. This method display table displays the table. Now let's see this method delete. This method will delete the record with this key from the table. As we have discussed earlier, to delete a record, we'll just set its student ID to -1. And if this key is not present in the table, then this method will return null. Now let's see this method main, where we are entering the initial size of the table and then we are creating this hash table object. Now we have this while loop. Inside this loop, first we display all the options and then enter a choice. And then depending on the choice, we'll call a particular method inside this switch. In case 1, we are calling this method insert for inserting a new record. In case 2, we are calling this method search for searching a record. Now if this method returns null, it means that the key is not found. Otherwise, we'll print the record. In case 3, we are calling this method delete for deleting a record. And in case 4, we display the table. Now let's run this program. This is our hash table. Now we search for a record. This is the record with key 69. We search for another record. Key 63 is not found in the table. We delete a record. The record with key 69 was deleted from the table. We've used linear probing here. If we want to use quadratic probing, then in all the methods we'll have I into I instead of this I. So here also we'll have I into I, and here also we'll have I into I. If we want to use double hashing, then here we'll have to use another hash function. Now earlier I told you that if the hash table becomes too dense, then its performance decreases. And in that case we do rehashing. So now let's see the modified program. We have created a new method, insert1. In this method, we perform the insertion by calling this method insert. In this lecture, we'll discuss separate chaining, which is a collision resolution technique. In this technique, we'll maintain linked lists for records that are mapped to same hash address. So here, each slot of hash table will refer to a linked list of all records that have same hash value. Any index I of the hash table will refer to the linked list of all records that have hash value I. Now let's understand with the help of an example how we can resolve collisions using separate chaining. These are our keys. We have used this hash function and we have this hash table of size 7. We can see that the keys that are mapped to same location are stored in a separate linked list. These two keys are mapped to location 0, so they are in this linked list. These 4 keys are mapped to location 1, so they are in this list. This key is mapped to location 2, so it is in this list. These 3 keys are mapped to location 4, so they are in this list. And this key is in this list. So keys are stored in respective lists depending on their hash addresses. Now let's see how insertion deletion and searching is done. For inserting a key, first we'll evaluate the hash function and get the hash address. Then we'll insert the key in the beginning of the corresponding linked list. For example, suppose we have to insert this key in this hash table. First we get the address, this map to location 4. So it will be inserted in this linked list. We insert it here in the beginning of the list. Now let's come to searching. For searching a key, again we'll evaluate the hash function and get the hash address. And then we'll search the key in the corresponding linked list. For example, suppose we have to search this key. We get the hash address. Hash address is 1. So we'll search for this key in this linked list only. Now for deleting a key, first we'll search the key and then we'll delete the node that is holding the key from its linked list. Now these linked lists are referred to as chains, and we have a separate chain for keys having same hash address. So this technique is named separate chaining. Now let's analyze the performance of these operations. The time to compute the hash address of a given key is constant, and we are inserting in the beginning of the list. So insertion is a constant time operation. In the case of searching, finding the hash address again takes constant time, but searching through a list takes time proportional to the number of items in the list. So the searching time depends on the length of the lists. If the lists are short, searching time is less. But if lists become long, then it takes more time to search a given key in any list. If the distribution of keys is uniform, it has been shown empirically that the average number of keys per chain is roughly proportional to the load factor. So on an average, the list length is equal to the load factor. We have seen that the load factor is defined as a ratio of number of records and the size of the table. In case of unsuccessful search, we have to go to the end of some list. So we'll have about lambda comparisons. For successful searches, we go about half the way down some list. So on average, the number of comparisons in a successful search is this. So we can say that the runtime complexity of separate chaining is this, where this lambda is the load factor. The worst case is when all the keys hash to the same chain, and in this case the search time becomes order of n. This method, separate chaining, is useful in dynamic situations where the number of the keys is not known in advance. Hash table never overflows. You can always insert more elements in the chains. Another advantage of separate chaining is that deletion is easy. No special flag values are required. To improve the retrieval performance, we can maintain the lists in sorted order. This is useful if there are much more searches than insertions, and if most of the searches are unsuccessful. The main cost of separate chaining is the extra space required for maintaining the linked lists. Now let's see how to choose the table size in separate chaining. This method is generally used in cases when the number of records is not known in advance. So the choice of table size depends on the memory available. If table size is too large, then there will be many empty chains, thus wasting large area of memory. If table size is taken too small, then the chains will be too long and the searching will take more time. Generally, table size is chosen such that n by m is equal to 10, where n is the number of records and m is the size of the table. In this video, we'll see implementation of hash tables using separate chaining. We'll be storing student records in a hash table. So we have made this class student record. It is the same class that we saw in open addressing implementation. This class node represents the node of a single linked list. We are going to store student records. So this info is of type student record. This link refers to the next node of the linked list. Now this is a single linked list class. We have already discussed various operations on single linked list in the linked list section. This method will display the list. This method searches for a value in the list. This method will insert a new node in the beginning of the list. And this method will delete the node whose record has this key value. Now let's see this hash table class. We have this array of type single linked list. This m and n as usual represent the size of the array and number of records. These are the two constructors, and this is the method that implements the hash function. Now this method display table displays the hash table. Inside this method we have called this display list method of the single linked list class. Next we have this method search. First we map the key to a hash address using this method. Now we search the key in the linked list corresponding to the hash address. And for this we have called the search method of the single linked list class. Now let's see this method insert that inserts a new record in the hash table. First we extract the key from the record. Then we map that key to a hash address using this method. And then we insert the record in the beginning of the corresponding linked list. This method deletes a record from the hash table. We map the key to a hash address using this method, and then we delete the node containing the record from its linked list. And to delete a node from the list, we have called this method delete node of single linked list class. Now let's see this method main. Here we are entering the initial size of the table, and then we are creating this hash table object. Now we have this while loop. Inside this loop, first we display all the options and then enter a choice. And then depending on the choice entered, we'll call a particular method inside the switch. In case 1, we are calling this method insert for inserting a new record. In case 2, we are calling this method search for searching a record. If this method returns null, it means that the key is not found. Otherwise, we print the record. In case 3, we are calling this method delete for deleting a record. And in case 4, we display the table. Now let's run this program. This is our hash table. We'll search for a record. We'll search for another record. This is not found. Now we'll delete a record. So the record with key 11 was deleted from the table.